Okay, so I'm just gonna return to summarize where I was last time. So I finished dealing with the sort of filters for well-formed structures that have to do with general properties that are not language specific, like head structural head specifier complement and phrases and labeling. And all of these can happen in this I language that's prior to externalization to specific languages. But then you come to this externalization phase where two main things happen. One is that your tree structure, like freely floating non-planar tree structures, need to be planarized so that you get an actual order sequence of words that give you form sentences. And this choice of planarization itself has to necessarily be language dependent. There's no canonical unique way of assigning a planar structure to trees. And this is the content of this section of it. So there is a natural canonical projection the other way around that forgets the planar structure of trees, but we're actually trying to climb up this projection, and there's no canonical way of doing that. So any way that you choose is going to be dependent on a specific language. But then that's not all that happens. We also know among all these trees for which you can choose in whatever way you want a planarization that does not violate any of the word order constraints of one particular language, which are learned and acquired in language acquisition. So at this point, anything that does not violate any of the word order rules would work. But then still a lot of structures are going to die out in this quotient here because some of them violate other specific rules of syntax of specific languages, and so only some of them will survive in these other sites. And so what basically says what is compatible with what and what survives in the end is something that has to do with ways of describing the specific syntactic variation across languages. Everything that we've discussed so far is kind of independent of this, but ultimately, we do see a lot of specific variation in the syntactic rule of different languages, and this is where all of those are playing a role and get encoded. So yeah, let me just skip the parts that I have already talked about, and so what I measure is that one phrase this idea of externalization in terms of this kind of correspondences, when you are comparing, doing these comparative studies of syntax across languages, you can think of it in these terms of being comparing different ones of these externalization correspondences and how they can be related to each other. And yeah, so let me come back here to say a little bit more about how people try to understand the specific variability of syntax across different languages. And since the 1980s, there's been this idea of trying to parameterize the variability of syntax in terms of a set of binary variables that would capture answers to basic yes/no questions about whether certain kind of syntactic constructions are allowed or not allowed in a given language. And one of the problems that have always been there from the start with this parameters problem or parameters principle is that it's one doesn't a priori know what is a sufficient number of variables that you need to know to pin down completely the syntax of a particular language. And also, if you have many of these variables that of course come out of like natural questions about the way the syntax is described, I'll show some examples in a moment. In general, you don't know whether these really are good independent variables or not. In fact, there are lots of reasons, which I'll discuss, to believe that in general, they're really not independent variables. So they're kind of really overshooting this by, there are, one can construct hundreds of these parameters. And right now, so it is believed that in the very early developments of these parameters principle, this model of syntax, it was believed that some kind of maybe the order of 20 something parameters or so would actually be enough to pin down the syntax of a language. And as time passed, people realized more and more that the syntax of a language has many different aspects, and each one of them is governed by its own parameters, and there's some kind of hierarchies of parameters, and I'll say more about that. Some of them have to do with micro variations, so variations that happen in languages that are otherwise very similar to each other. Some of them are like more global, and they describe larger scales that are across languages of many very distant families. So there's a lot more structure in this idea of parameters. And at the moment, it is believed that people that have been collecting a lot of data about specific variability of syntax across languages, that you can come up with something of the order of at least 200 parameters and probably more, but at least it's the order of the hundreds and not the order of the tens. And so you have this it means that there's a very big ambient space, which is this binary, binary vector space of some very large dimension n, where each coordinate is one of these possible syntactic parameters. And inside this very large space, there is some subset, which we don't know how it's structured. We don't know what kind of set it is, but it's the region that is occupied by actual human languages. So it's clear that these parameters that are known, you cannot just arbitrarily assign the values to be zeros and ones in whichever way you want. Most of these combinations would not correspond to anything that looks like a known human language. When you try to place the points that known human languages occupy, they actually occupy a much smaller locus inside this enormous space. And so one can say that there is a space of possible languages, and there's a region of impossible languages, and you sort of like to try to cut out this locus in come up with some kind of efficient description of what the locus of actual possible languages is. There are interesting experiments that linguists do. So you can hook up some fake language, like with invented words, and you make up some rule of grammar, just invent some rule of grammar. And you can do it in a way that sort of resembles some actual human languages, maybe completely different from the one that the speakers, that the people you test it on will be speaking, but still something that exists in human languages. And you can ask people to guess the rule on the basis of simple examples where it's applied and in a completely invented language. So you just see some words and you have to guess a rule. And it turns out that it's very easy for people to guess if this rule actually corresponds to something that exists in some language. And it's very hard to guess if it's a rule that's completely made up that corresponds to some other region that's very far away from where actual languages live. So this is a kind of experimental evidence that is used to kind of support the idea that there is some things that our brain preferentially recognize as languages and some things that our brain does not recognize as languages. There have been some interesting study recently that there's slightly conflicting evidence or conflicting conclusions. So I don't think these studies are entirely conclusive, but about to what extent, if you look at how language is handled by things like the large language models, whether they do make any distinction between the possible languages and the impossible ones. And the most recent result that has come up on that question seems to see that there's some kind of gradual response. So that if you things that are not quite in what we as humans recognize as the possible human languages would be reasonably learned, no, but things that are really far away were not. So sorry, the other way around, that no, for us, so this is what happened for humans, right? But for large language model, there's a slight change, but it's much less significant, and you have to go to something that's very, very far away from for the performance to change. Whereas for humans, it's a very kind of much more clear-cut thing what is recognized by our brains as a language or not. So that's this kind of point of view is sort of sense useful to try to understand to what extent the handling of language in machines is modeling or not modeling, is modeling something, but is modeling or not modeling, the human handling of language. So in terms of what the way we can see the situation here, as I said, we are somewhere in this in this space of all possible planar trees, and we're trying to project down to subspaces where we kill off things that are not compatible with some syntactic parameters of specific languages. So it's like if you have a set of string of syntactic parameters, the way they're set for one particular language, these cut out certain particular vector spaces here. I mean, of course, you're looking at a specific basis element, right? The particular tree, is this compatible with language or not? So it's a bit arbitrary whether you want to think of this as a quotient space or a subspace, because you're just looking at basis element and saying this is okay or this is not okay. To think of it as a quotient, I'm throwing away the ones that are not okay, and if I think of it as a subspace, I'm identifying the ones that are okay. I mean, it makes a little bit of a difference, right? Because if we think about how we learn a language, we are only exposed to positive examples when we are learning a language. As a child is learning a language, it's not, they do not learn it by saying this sentence is not good. They learn it by saying this sentence is good. So maybe there is a slight difference between whether you want to think of it as a subspace or as a vector space, right? As a quotient space. But anyway, it's like,
that depends on the parents.
That depends, yes. but anyway, you can think of it as each setting of parameters is selecting a certain subspace in this space of all possible subspaces of my So what about so I'm going to say a little bit more about what is known in general at the moment about these syntactic parameters. And of course, look, Sita has already been exposed to all of this for a long time. But okay, I mean, there's various databases where linguists have been collecting data of syntactic parameters about languages, and as I mentioned at some point, of course, compared to collecting databases of lexicon, like collecting vocabularies, this is a much harder kind of job, because you're not just making lists of words, you actually have to test whether certain syntactic constructions are used or not used in a particular language. And of course, there are languages that an enormous number of people speak that are very well classified in terms of what their grammar looks like and so on. And there are languages that have very few speakers, and where this kind of work has to be done in a very slow, and so these databases grow very slowly. Every once in a while they get updated but and they tend to, of course, be much more complete on certain families of languages that are much better studied than others. The Indo-European languages tend to be overrepresented with respect to how many languages, Indo-European languages, there are in the whole set of world languages. So they usually, everything that has to do with this type of linguistic studies is historically biased towards the Indo-European languages because they're more widely studied. But they now include several languages from other families, but some of them are not completely mapped given the number of parameters. So dealing with this data is always a bit tricky because you have this incompleteness and you have these biases. But maybe there are some of these. So one thing, of course, that you can do, like before trying to build theoretical models about how this externalization depends on syntactic parameters and how syntactic parameters work and so on, you try to like look at what data the linguists have and try to throw some very basic data analysis at that and try to extract some information from these. Now, for example, right, since one of the main questions is how many variables do we really need, and where are those variables that we actually need? And this is a typical kind of question of data analysis, because typically the data that you're interested in occupy some much lower dimensional submanifold inside the space where you're classifying them. And you want to try to understand that manifold. That's one of the main aspects of data analysis. And various kind of methods, mathematical methods that these days are very fashionable for doing this kind of thing. So just to kind of get, without going into the specific details of comparative syntax, I just want to show what are the kind of things that people try to classify. And so the syntactic structural world languages, the SWL database, currently has around 250 languages that are represented and 116 parameters. And these are actually grouped together in various substructures that try to describe different kind of properties of syntax. There's the first block of parameters just have to do with word order properties, and whether subject verbs, subject object verbs, relative positions of elements in the sentence, and have to do with with this planar structure of the tree. So there would be the kind of parameters that influence the first part of this externalization process that just chooses the order, your planarization of trees. But then there's many other things that have to do with how you choose auxiliaries for verbs, how you form the negation of a sentence, how you form the turn a sentence into a question, and the other things that have to do with keeping track of number of gendering words or so. There's a lot of them would probably qualify as morphology rather than syntax, but as I was saying, that the boundary between syntax and morphology is more about like how much you're zooming into the structure of words and making them part of the structure of sentences. So there's no clear-cut boundary between. So when you look at parameters, some of them look more like they are describing morphology. Some of them look more like they're describing syntax, but in fact, they are all describing this morphosyntax, combined object. And so this is an example of a set of different properties that are being analyzed in some of these databases. And one can say, okay, is this everything? Well, no, it's really not everything. Like for example, there is this other complementary data set, which is this collaboration in England that has collected them. And here it's only a group of 64 languages, most of them Indo-European with a few exceptions. And I think there's like 2 Dravidian languages and some Sino-Tibetan, and but there's a very small number of non-Indo-European languages, all the other are Indo-European. And again, these have to do with other properties of syntax. And in fact, these 2 databases, fortunately, can actually be considered as sort of independent. So one can combine the data and make a study of both of them at the same time. But so and these are 83 other parameters in addition to so this already accounts for about 200 parameters. So you're already inside a space which is 200 dimensional. And so at the moment, the best study of syntactic parameters is in this recent book of Ian Roberts. And it has good thing that it is already formulated within this minimalism framework of syntax of generative, the current version of generative linguistics. It has a very extensive empirical evidence of syntactic variation across languages, so it uses a lot of data. And it's sort of one thing that it's trying to describe is, in addition to just listing parameters, is certain kind of hierarchical structures among parameters, in the sense that some of them are looking at more small scale variations in languages that have otherwise tend to be very similar, but that have microstructures in which they differ. These, for example, are good for studying. So the micro variations that are studied are, for example, when you have a lot of different dialects of a given language, and some of them end up being close to other languages. So you have, it's almost like a continuum of interpolation between two languages. And of course, the main syntactic parameters, they describe more macro structure, and they tend to be the same. Like Italian and French differ for very few of these main syntactic parameters. One of them is pro-drop. The Italian has it and French does not. But will be very hard pressed to find essentially any other differences in this. But if you go into these more micro parameters, then there is indeed a continuum, almost a continuum of in between languages that are geographically distributed across the border between these two countries. And so that allows also for this kind of studying of how languages differ on smaller scales. And one thing that this book suggests is that also parameters should be treated to some extent as some kind of emergent properties, where you have this overall mechanism of language production, which is language independent that we described. And then you have constraints that are coming from what you are exposed to in learning. And again, some kind of optimization property in computation, which for example, would tend to tell you that if you have two competing constructions, that for example, if people that are exposed, that are bilingual, are exposed to two different languages that have parameters in a somewhat different way. If you have two competing constructions available, if one of them tends to be less more simplified in some sense, of making your computations more efficient, and then it tends to prevail, or some dynamics like this will take place. But the main problem of this, of what is available at this point, is that there's a very extensive description of how things are in terms of variation, syntactic variation across languages, but there's no good theoretical model behind this syntactic variation. So that's one of the aspects of the model that is still, in a sense, under development. So I'm going to just say a little bit more about what one can say at this point about this, how these syntactic parameters behave, right? So these are just things that you can extract by analyzing the data that are available so far about syntactic parameters. So one thing is, I said, we've seen that these are dynamical variables. They evolve. Syntactic parameters. Syntax is a very robust quality of language, so it doesn't change easily, but it does change. And over time, there's in history, there's been well-recorded phenomena of languages like Sanskrit, for example, that have switched syntactic parameters a few times in history by interacting with another language, very different language family known in the European language family, that is the Dravidian languages. And so there's been there's some evolution that has to do with interaction of languages and so on. And of course, we can trace the development of languages. That's something that historical linguists have been doing since the 18th century, at least. In fact, even much earlier in antiquity, but they say in modernity, that there's been already some centuries of trying to understand which languages are more closely related to which, and how and hypothesizing evolutionary trees that take you all the way to some proto languages like the original Indo-European or something like that. And usually these studies historically have been done on the basis of comparing how the lexicon changed and comparing how morphological rules for inflection of names and conjugation of verbs have evolved over time. But so one can see how much the information about how syntactic parameters differ in languages that are related in the same historical family correlates to what one knows from this other kind of evidence about the actual phylogenetic trees of a certain language family. So normally, if you, the null hypothesis for this would be that each of these binary variables, so if this were actually, a good set of independent variables, right, these syntactic parameters, you would expect that each of these binary variables would be evolving as some kind of Markov model along a tree as your, as languages are evolving, so that they would be identically distributed independent random variables that, evolve according to a Markov model on a tree, and that the distribution that you see at the leaves of the tree, which are the syntactic parameters of the current languages in a given family, should reflect what has happened according to this kind of evolution, tree evolution. In particular, one knows that if you have variables that are behaving like a Markov model on a tree, then you should be able to reconstruct the tree to some good extent, or at least evaluate the optimal possible tree on the basis of the distribution of these variables at the leaves. And there's various methods for doing that. There's some that are more statistical, some that use algebraic geometry, so phylogenetic algebraic geometry, and so on. These have been developed largely for applications to biology, but you can try to apply them to this. But I mean, it turns out that if one compares what you get by a model like this and the actual phylogenetic trees of languages, there's some discrepancies. Discrepancies happen both when you have incorporate languages that are sufficiently far away from each other in relatedness, in historical relatedness, but also when you look at languages that are very closely related, like this microvariation in historical relatedness. So this is something that Sita has been working on, and this, one finds that indeed there is a detectable discrepancy from this Markovian behavior. And that is indeed a way of detecting the fact that these are not independently equally distributed random variables, because there's an enormous number of relations between them that affects the way that these can evolve as variable. There are other ways in which you can see this same phenomenon. And I'll show you one just for fun. For example, if you take a collection of languages and you want to compare their syntactic parameters, so each language has a string of binary variables, which is the setting of the parameters of that particular language. So if I'm comparing a group of, say, I don't know, 10 languages, I get 10 binary words, and I'm looking at how they compare to each other. So I can think of this as a binary code. It's a set of 10 binary code words. And of course, I can use some methods from mathematical coding theory to say like how far away they are, these code words from each other, how this code would behave as a code, and that tells me something about the relatedness of these words. And again, this is something from which you can test how a kind of random variable model would behave. Because if I have codes that are randomly generated, like there's something that called, usually one calls the Shannon random code ensemble, where you have code where each letter is an independent, equally distributed independent random variable. So your codes are just done by throwing the dice or well, a coin if it's a binary code, and filling in the words. But if those were obtained that way, then they would tend to populate only a certain region in the space of code parameters that tell you how well the code behaves in coding theory. And when you actually do it with the data of syntactic parameters, you see an enormous number of outliers that are way up from where they're supposed to be with respect. I mean, of course, you see a lot of them that are where you expect them to be if they were, but you see enough of them that are outliers that, again, it shows that these there are relations that are a lot more structured than this random random code ensemble. And so another thing that you can do is there's various ways of doing dimensional analysis on your data. Like if your data is lying on some manifold inside a very large dimensional space, what you can do is look at how a ball grows right around your data point that incorporates other data point, and the volume of the ball kind of grows differently according to what dimension you are in. And so you can give, it gives you an estimate of what is the actual dimension that your data are occupying, which can be much smaller than the one of the ambient space. And if you do it for this set of parameters, you find that, for example, if you look at these 116 variables of the assess.wl database, only about the actual estimated dimension turns out to be only about around 30. And if you do it for this other set of parameters of this link collaboration, you find that out of this 83 variable, there's only about 15 of them capture the actual dimension. So in a sense, this is suggesting that this original guess of this principal and parameters model that was saying that maybe just a few tens of variables would actually be enough to pin down the syntax of the language was not that far off. Because now, people kept looking at it and they kept finding hundreds of these parameters. But when you actually look at the dimension, it seems that it's still down to something that is not in the order of the hundreds. It's still in the order of the tens, except that you don't know what those variables are. Okay? And that's one of the main questions about this type of data analysis. You can see that the actual space would be so much lower dimensional, manifold variety, but no, you don't have a concrete hold of what that is. And there are other tests like this, like for example, if you try to think about how well, of course, one of the main, so what I described so far is like one of the main questions about this principal and parameter model. What are the actual variables, and what are the relations between the variables that are used? But another question is how is there like some good model of how this setting of parameter would actually be realizable inside our brains? Where are these parameters stored, or how can they be stored? So of course, one can try models of distributed memory that have been used in the past by neuroscientists to try to make models of how we store memories in the brain, or we store information in the brain. And for example, one thing that we looked at some years ago with some of my students was that if you look at these models for sparse distributed memories, kernel networks where you can store data in such a network. And then, for example, you can, so these have, one of the properties they have is that if your data gets corrupted, but not too much, it will be recoverable from the network. And so this is maybe a reasonable model for it, saying why fewer variables work, because some of the other we actually store something that where many things are reconstructible from the others. And in fact, if you try just make such a computational model, you try to store this data of syntactic parameters in a kernel network, you'll find that some of these parameters are much more recoverable from the others than others. So it's like some of these are much more dependent variables. So there are a lot more dependencies on the other ones than others. So these are all things that one can just see by looking at the data and try to torture the data until they tell you something. And so let me just for example say a little bit more about one of these examples, right? So I mentioned this thing about comparing languages by thinking of them as a binary code. So what did I do here? I choose a set of languages in my database, and I can just do like random sets so that I don't just compare things that are in the same subfamily, or I pick like randomly generate sets of 3, 4, 5 languages and look at the comparison of their syntactic parameters. So for each group of languages that I choose, I get a binary code, which are the list of their syntactic parameters. Now, I mean, I try to look at what this looks like as a code. So generally in coding theory, there are two main measures that one assigns to binary code that are trying to tell you how good this code is or not. And of course, the code has to do two things, encoding something and decoding something. So one of the parameters is trying to keep track of how good the encoding is. and the other parameter is trying to detect how good the decoding is. So so on the basis of where each code is giving you a point in this plane with these two parameters, code rate and code, the relative minimum distance. And depending where you are in this plane of code parameters, your code is bad or good. If you know, ideally, of course, you would like to make the code that is very good for encoding and very good for decoding. And there's a tension between these two things. In general, you cannot get both of them, simultaneously, because of course, good encoding in some sense is based on having more redundancy, but good decoding relies on your code words being very sparse, so that if there's an error somewhere, it's easier to identify where it should have been. So these two things, of course, are in sort of tension with each other. The more redundancy, the more you're filling in code words, and the more it's unlikely that they are very distant from each other. So that's a way to think of this. So that the transmission rate of the code is simply the logarithmic size of the code compared to the length of code words. And the relative minimum distance is the Hamming distance between words. So like how distinguishable they are. And then you take the minimal, the minimal Hamming distance among all possible pairs of words in the code. And so this, of course, is good decoding, because if they are sufficiently far away, then you're more likely to be able to pick the correct word in the presence of not too many errors. And so a lot of the theory of coding, especially the asymptotic theory of coding, where you allow the code words to be quite long, and is about getting bounds on the relation between these two parameters. And there are several kinds of bounds that one knows about. So one thing is there is a curve that is called the Gilbert-Varshamov curve that has to do with the Curie entropy of the code. And it's essentially, the entropy is there because what you're looking at is the volume of the Hamming balls. So it's a way of saying like how far away your code words are, is like, how they are distributed with respect to looking at the ball around one of them in the Hamming distances. So the asymptotic behavior of the volume of the Hamming balls is the Shannon entropy. And so this Gilbert-Varshamov curve is actually the one that does represent the typical behavior of the random code, the Shannon random code ensemble. So if you have the codes that are randomly generated, they tend to populate the region in this space of code parameters that is at most as high as the Gilbert-Varshamov curve. So at best you can meet this bound. And there are other bounds. For example, there's this Belkin curve, which is again based on relation with the Hamming distance, and so that there is a much rougher, higher bound. And there's a more significant bound, but that's very hard to pin down explicitly, because unlike the Gilbert-Varshamov curve and this Belkin curve, it doesn't have an explicit expression for this function. It's the asymptotic bound. And it's simply saying that when your code becomes very, very long, in the limit of very long code words, you can separate out two regions in the space of code parameters. One of them below this asymptotic bound, where the code points are dense. And so code points are actually points of parameters R in delta that are realized by some code, maybe with very long code words, but are actually realized by some code. And are not only they are dense, the code points, but they're also, all of them have infinite multiplicity. So once they are realized by code, they are longer and longer codes that will realize the same code points. But if you are above this asymptotic bound, then the number of code points is discrete, and they have finite multiplicity. So one can prove that there is such a bound, and also that it is contained between this Gilbert-Varshamov curve and this Belkin bound. And so there are like nice kind of physical type interpretation of this bound. There's some kind of phase transition in the space of codes and so on. But in general, no, people that work in coding theory for whose goal is to construct optimal codes, and one of the goals is to actually be able to construct family, have constructions of codes that are as high up as possible, so in particular above this asymptotic bound. What is known from coding theory is that often these codes are highly rigid in the sense that they come from algebra geometric objects. So for example, they come from counting points on curves over finite fields. But for example, the only explicit constructions that are known are for very large cardinality of your field. So your code alphabet, instead of being binary, is some Q that's bigger than 49. So it's very hard to get explicit constructions of codes that are above the asymptotic bound. The problem for binary code is a very interesting one. It's expected that there should be an explicit construction of optimal binary codes above the asymptotic bound coming from expanded graphs and things like this, but this is kind of expected, but there's no good construction. So I'm saying this because when you start to do what I said, you sample this data of syntactic parameters, and you see, if you look at comparative syntax as a code, where these codes actually are. And so the first thing you find is that you find some stuff that's down at the bottom of this diagram. This will be things that does behave like random codes to some extent. And at first, when you can plot these things, you see this kind of apparently strange looking fractal-like structure. But this is not mysterious. This is actually something quite simple. And what this is the graph of this function, which is called the Tomare function. And what you see is that as you keep plotting this thing, you see like you can identify the plots that you get as a superposition of a few of these Tomare functions. So why do I see these Tomare functions? So these are, if you take a rational number, written in reduced form, it's 1 over the denominator for such a number, and 0 the rational number. So it's a very irregular function. But the reason why you see these things is because once I've chosen my set of language that I'm going to do a comparison over, I'm fixing the cardinality of my set of words, right? So I'm fixing this k, which is the logarithmic size of the code. And once I fix my k, then of course n is going to be the length, but here one has to remember that these data have lacunae. So if you look at the SSWL database, it is 116 variables, but when you are comparing, if I pick randomly 5 languages in this database, not all of them will have all these 116 parameters simultaneously mapped. There will be some intersection of parameters mapped for all of them. And so your code has the length, whatever that length happens to be, because that's the data you have. You cannot work with the data you don't have. So that means that this M is actually dependent on which set I'm looking at. And so, but once I have fixed this, and then I have fixed one of these coordinates, and all I'm looking at, which is the variable that I'm really interested in, it is the Hamming distance between this. So for each of these, I do see one of these Tomare function, because this value is fixed, and so that's the reason why I see this. So this part is not surprising, and the part that is more surprising is how far these functions extend. And the things that, this is your Gilbert-Verschamow curve. So everything that's happening here is compatible with this idea that this would be identically distributed independent random variable, these binary values. But what starts to happen here, and especially what happens here, so if you are above the plotting bound, you're above this asymptotic bound. So these are these kind of codes that everybody is looking for, right? And here they are, and you see that there's quite a lot of this. So it seems like this is saying that there are some serious violations to the idea that these are, you know, identically distributed and independent random variables. And so this is one of the ways that you see evidence of the fact that the structures in the relations between these parameters that are, you know, probably keeping these Hamming distances, that force these Hamming distances to be bigger than they would normally be if this were, you know, randomly distributed variables. And, you know, again, as I said, you know, if you look at the dimension, you know, there's this big drop in dimension, which also, of course, is due to the fact that there are relations between all of these variables. You can see by this same method that if you restrict to specific language families, there are only 2 language families that have enough representatives to do this this reliably in the SWL database, the Indo-European one, of course, and the other is the Niger-Congo languages, because that's anyway the biggest class of languages in the world. And for these ones, the drop is even bigger, which means that in addition to the relations that you have between the syntactic parameters, there are language-specific family-specific relations, which, of course, to some extent, we already know that languages that are in the same language family, they tend to have more commonality. And this is further reflected by the fact that there's an additional drop in dimension when you look at the data of specific language families. Okay, so now next thing one can try to do with these variables that are available in this data is to actually try to see if one can come up with some other variables, right, that would describe as much as possible of the variance of this data, and that would definitely be independent variables that one can look at. So, of course, it's another well-known kind of problem in data analysis. You want to look at some, lower dimensional projections of your data that try to capture as much as possible of the variance that you have in your data. Of course, one very, very popular way of doing this is something like principal component analysis. And that's kind of a linear algebra, projections, where you try exactly to find. I mean, you can think of it this way. That imagine I have a 3-dimensional object and I want to project it to 2-dimension. So I start to look at what is the direction in which you have the maximal variation in this in this thing, and I take that as my first direction in which I'm projecting, and then I continue like this. So basically, when I do my projection, I'm going to lose something necessarily, but I try to lose the thing that has the minimal possible variation, so that I lose the least possible. Right? So that's in general. But I mean, that's not the only way to do this kind of low-dimensional projection. There are more efficient way than principal component analysis. So, for example, there's a method that's also quite well known and very commonly used in data analysis, which is based on the geometry of the Laplacian. And so this was introduced by Belkin-Niyogi, and it's mapping by eigenfunctions of the Laplacian. So the idea is something like this. You have some ambient space where your data are embedded, but you think that your data are actually points that are sampled according to, so that they are sampled from lower dimensional submanifold. So you think of your ambient space just as some Euclidean space. And inside this Euclidean space, you have some manifold of some much lower dimension. And the data points really live on this manifold. And you think of them as being randomly picked with respect to a probability distribution that is coming from the volume form of the Riemannian metric on your submanifold. And so your sample points according to this to this Riemannian metric. And so the idea is that you can build a graph from these points, and you can build a graph by the distances between points, or growing the radius of distances between points, or by nearest neighbors, meaning you put an edge to whatever are the first thing that your point will connect to, no matter. So this can happen not necessarily all at the same scale. So you get growing the scale until then you look at what are the first thing that a certain thing gets connected, and then what are like the second neighbor and so on. So you can form some graphs of connectedness that have to do with that depend on the geometry of the manifold in which the data are embedded. And the key there's a key geometry result here, which is the fact that if you form a graph in this way from a sample of a submanifold according to the probability distribution given by the Riemannian metric on that manifold, then the graph Laplacian on this discrete graph will converge to the actual Laplace-Beltrami operator on the manifold as the sampling of points becomes dense in the manifold, so going to the limit of infinitely many points. And so, given these results, which I'll say something about it right now, but then it means that one thing you can do is to form a lower dimensional projection on the basis of using the eigenfunction of the Laplacian. And I'll say a little bit more about why that's a good choice, why that is likely to give you a good lower dimensional projection. And the thing is that now you can use the Laplacian of this discretized structure that doesn't require you to know the manifold, only to know the discrete data point to get this lower dimensional projections. Yes.
Should you use the graph explicitly, because then you need the metric.
Right. So that's right. So at some point you have to use an approximation because you know the metric in the ambient Euclidean space. You don't actually have explicitly the metric on the manifold, but you are assuming that if your points are sufficiently close on the manifold, then you have an order of approximation if you replace the path on the manifold with the path in the ambient Euclidean space, and you have to show that in this limit that order approximation that just gives you something that goes to zero, so that you can use that. Yeah. So let me just say a little bit more, how this works. I just explain the main idea right now. Let's say a little bit more how that works in practice. So you are inside some large Euclidean space. In a Euclidean space, you have your standard flat Laplacian and this corresponding heat equation. The solutions are given by the heat kernel distribution. So the solutions are coming from the equation are coming from convolution with the heat kernel. And here the metric is the metric with respect to which you take the heat kernel. This is just a flat metric in Euclidean space. And you can use the heat kernel as a way of describing the action of the Laplacian, because if you take your act with the heat kernel and then you take the derivative with respect to the parameter of the heat kernel and set that equal to zero, then you obtain exactly the Laplacian. So knowing that, this is just to say that if you want to describe the Laplacian, describing the heat kernel gives you that as a bonus that gives you back also the Laplacian. And so this means that you're looking at the limit as this t variable of the heat kernel goes to zero of something that depends on convolving with the heat kernel. And so the thing is that if you want a good approximation for the Laplacian, you can think of it as being a good approximation of the heat kernel. And so choose some uniform sampling over your manifold with respect to with respect to the volume form on the manifold, and you know approximate the heat kernel on the basis of these sampling. So you get something which is like a discretized analog of the heat kernel. It's discretized in the space variable. Now, the t variable is still a varying parameter with respect to which you're going to take the limit. Okay, so this is just in the Euclidean space. So far there's like no manifold taken into account. So when I say the sample, just sample with respect to the Euclidean space here. But so when you do this on a manifold, you're thinking of the manifold as being embedded in a Euclidean space. So you are using an explicit embedding of the manifold. It's not like an abstract Riemannian manifold. It's an embedded Riemannian manifold with a fixed choice of embedding. And then it's true that you can approximate. If points are close enough, you can approximate. I mean, the distance on the manifold is going to be bounded below by the distance in the ambient Euclidean space, but you can it's bounded below by something that goes to zero as the points are close to each other. And so you can well, first of all, if you're looking at the limit for points that are nearby, you can just forget about look at the entire manifold. You're looking at some small open set around the point. And so you can parameterize the coordinates on the manifold by the exponential map from the tangent space at that point. So you're really dealing with the tangent space of the manifold and the corresponding Euclidean space. And the exponential map is also relating, when you do this parametrization, is also relating the Laplace-Beltrami operator on the manifold with the Laplace-Beltrami operator on the Euclidean space. And so there's something that plays a role here that still detects the discrepancy between this Laplace operator on the manifold and Laplace operator on the Euclidean space, which depends on the curvature, and it depends in particular on the scalar curvature. So your exponential map is locally invertible until you reach the injectivity radius of the manifold, where the map from the tangent space is no longer one-to-one. But if you're small, in a small neighborhood, it is invertible. So you can always choose coordinates that are coming from the tangent space, mapping things back to the tangent space, and look at geodesic distances in that way. And so when you look at you compute the Laplacian, the Euclidean Laplacian, and compose with the exponential map, you have a term up to something that's of the order of the norm of the vector. You have something that depends on the scalar curvature. So when you look at the Laplacian, the flat Euclidean Laplacian in terms of these exponential coordinates, you have some term that's depending on the dimension of the okay, but also explicitly on the scalar curvature. But the thing that helps here is that when you are comparing, this when you're taking these limits of the heat kernel, you're looking at the difference of terms, and the contribution of this term with the scalar curvature is actually going to cancel out. And this is exactly what allows you to make this trading of the distance on the manifolds with the distance in the Euclidean space, is that the correction terms that you would have, that you would pick up by the scalar curvature, is actually canceled out because you are only looking at these differences. So you can actually do that. And so the result is that is this theorem that I have in this paper of Belkin-Niyogi, that the graph Laplacian, which is is obtained in this way from this discretized heat kernel, is in the limit giving you the Laplace-Beltrami operator on the manifold. And so this, of course, as I said, you've really defined a discretization of the heap kernel rather than a discretization of the Laplacian, but you can get one from the other. As in the continuous case, you can get the Laplacian from the heap kernel. And so the punchline is that if you have a set of sample data from the uniform distribution on a Riemannian manifold embedded in a Euclidean space, then you can reconstruct the Laplace-Beltrami operator on the underlying manifold or let's say the Laplace-Beltrami operator on the underlying manifold is well approximated by this discretized form, provided that you have a sufficiently large set, a sufficiently large point cloud of data. So why is this Riemannian geometry fact actually useful for these low-dimensional embeddings? Okay, so suppose that I have my Riemannian manifold and I have a map to the real line. And if I have points that are nearby on the manifold, these will map to points that are nearby in the line, provided that the gradient of the function is sufficiently small in that region. So if I want to optimize the reliability of the information that I get, that points nearby will go to points nearby in the way I map it to. Also, mapping to R is mapping to some one of the lower dimensions in which I'm trying to construct the mapping. Right? So I'm trying to construct each dimension in which I'm projecting. So I want to try to do that in a way that it respects as much as possible the structure of what was close to what in my original place. And so I try to minimize the gradient of the map. But minimizing the gradient is the same thing as is related to the decomposition of the Laplace-Beltrami operator into eigenfunctions. And so you can, the eigenvalues of the Laplace-Beltrami operator are in fact obtained by a minimization process over the gradient of the Laplace. And you can do this gradually over the span of the complement of the previous eigenfunctions. So this is the sense in which if I use the Laplace eigenfunctions as my map to lower dimensions, so I start to map according to the first eigenfunction of the Laplacian, then I map according to the second one, and so on. I get something that is quite faithful to the way that distances were in the original manifold. Of course, this is now not a linear mapping, because I'm mapping to whatever function my eigenfunction of the Laplacian happens to be. So my images will look very distorted, but they will still preserve the proximity relations that I had in my original data. Yes.
Question. So each point on your manifold is a data point, and what exactly is the data point? Synthetic data?
Yeah, no, I'm just assuming that my data points are sampled uniformly from some manifold, right? So
this is for the general.
Yeah, that's right. So no, I'm simply, the point is that I don't know the manifold itself.
So my question is going to be: are there boundaries on this manifold? Or is this a closer? Yeah,
so of course, this is you're just making like a kind of simplifying assumption that the manifold is closed. The only way that you would detect if a manifold has a boundary in this sense of to a data cloud would be if part of the data are actually kind of supported on a boundary, but then you could take that as its own lower dimensional problem, right? Of identifying. Yeah, so it would be like saying, okay, my data really belong to two classes, a class that's sampled from an n-dimensional manifold and a class that's sampled on an n-1 dimensional manifold. And so you could say, okay, I try to, I guess both of them,
If you have a boundary, then the slopes are more important, right? Because of the divergence. So the grad square would not be Laplace, it would also have like a negative boundary.
Yeah, exactly. That's why in this argument, one assumes that your manifold is compact, so that you don't have to also include all these boundary contributions when you write the Laplacian you only have the scalar curvature term to worry about, but you don't have like second fundamental form type
Yeah.
terms that come into the picture. But I mean, you could always, I mean, if your data really are kind of in the, not lining up along a boundary, but they are in the interior of some manifold, you could always close up your boundary by adding something else. What it matters is that, they are on something that's n-dimensional, k-dimensional rather than ambient n-dimensional. So this means that, this suggests a kind of explicit algorithm, right? If you have a set of data points, sample that well, or you suppose that are sampled from some, Riemannian submanifold of a Euclidean space, which you don't know explicitly, but you explicitly know the points. So what you can do is build this graph Laplacian, or with this heat kernel weights, this kind of discretized heat kernel on a graph that's built from the data points and their Euclidean distances in the ambient Euclidean space. And as I said, there's different ways in which you can build a graph, but you do that and you compute this graph Laplacian, and you compute the eigenfunctions of this graph Laplacian. And then you do a low dimensional mapping that just maps these points to the corresponding through these functions that are the first m, if I want an m-dimensional projection, the first m eigenfunctions of this graph Laplacian. And the conclusion is that this will be a good embedding because these eigenfunction will be close to the actual eigenfunction of the actual Laplacian on the underlying manifold, for which one knows that this would be a good projection. Okay, so this is some way to get some functions, right? Some kind of explicit coordinates, real valued coordinates on your space of data, whatever those are going to tell you. Okay, so if one does this on the data of syntactic parameters, well, one thing that you find is, so you look at this data and you try to build these graphs, right? So you either you fix a radius of epsilon around each point, and you make this radius grow, and whenever two of these are to overlap, you draw an edge. So this is this epsilon neighborhood graphs. Or at each point, you look at what will be. So you make ball grow, but then you count what will be the first neighbors. And some of them will happen at some epsilon, some will happen at some other epsilon, but you build the graph like that: first neighbor, second neighbor, and so on. And so you see that and you look at the way how this clustering goes, right? As you grow these epsilon variables, like what goes together? Well, how fast these things are clustering, and and also to how connected this graph is, how many components this graph has, and so on. So you see that these data sets behave somewhat differently with respect to these properties. They kind of behave more similarly with these n neighborhoods, but they behave somewhat different with this epsilon neighborhood system. So the way that they look like embedded inside this ambient Euclidean space looks different. But it becomes a little more interesting when you actually look at what these graphs look like. So these graphs are going to connect together some of these syntactic parameters. So in a sense, is a way to visualize some of the relations between these syntactic parameters. So the first things that will come together will be the ones that are more strongly correlated across all languages. So they're the ones that are more, you expect are going to be strongly dependent on each other. And so if you look at this line data, it's for a while it's very disconnected, and then you start to see some separated clusters of parameters that are coming together, and then they coalesce into larger structures, and then it becomes progressively more and more highly connected. And one can look, I mean, there's certain kind of syntactic parameters that cluster together. And at this point, I don't have like a good linguistic explanation for why these parameters are exactly the first ones that correlate together. If you look at what they represent, they actually represent sometimes fairly different properties of syntax. And so this means that the same somehow these different parameters, they can have like more macroscopic effects than their explicit description in linguistic terms suggests. And the other times, one knows more precisely in what sense they correlate, in terms of linguistic explanation. Like if one does the same epsilon neighborhood clustering on the DSS-WL data, again, things are fairly disconnected, but there's a first cluster of parameters that start to come together, and then they remain fairly connected before they start connected to anything else. And these are all a cluster of parameters that have to describe how you make negation in sentences. And it's interesting that they're like different subgroups of these negation parameters. Some of them coalesce together first, and then the other join in. And they describe fairly different ways in which some languages, for example, some languages are tonal, and some of the Niger-Congo languages, they make a negation by a specific tonal intervention on your sentence. And others have to do with things that combine tone and something else, or that have infixes in certain words that make the negative, that expresses the negation. And then there's another cluster of these negation parameters that are of a different nature. They tend to express negation by certain particle and position in your tree structure with respect to the verb. And these form another cluster, and these two clusters merge. And the thing is that these properties are indeed fairly particular as describing these aspects of syntax, and they don't have particular influence on or immediate influence on other things like word order and stuff like that. So in this case, it's one where you do see that this is not surprising in the linguistic sense that this would cluster together first, and they also kind of activated only in certain particular language families, and not in others, but not all in the same language family. So it's there's some fairly interesting structure going on there, and some of it is visible. It's better visible when you do these nearest neighbor connections rather than this epsilon neighborhood. For example, you do see that there are certain parameters that are very, in terms of the structure of graphs, they are like a highly connected node, and others. So there's several different notions of centrality in a graph, right? There's centrality in the sense that like a big hub for airports, right? There's one where all this itself very highly connected to things that are not necessarily highly connected to each other. With like whatever this is happens to be, I don't remember which parameter it was, but I mean this has this kind of hub centrality. But there's other things that are central in the sense that a lot of paths that cross the graph will have to go through that. Right? And this is another that's slightly different, because they don't necessarily have to have a high valence. In fact, this notion of centrality is usually like bottlenecks, so things that don't have a very high valence, but where everything is forced to go through. And so there's other structures like that. And as you grow to like, this is not first neighbors, but second neighbors, connections, you see more of this structure where there's like high hubs, and there's more connected. So you do see some of the properties of what the relations look like in the SSWL database. It's even more interesting because it has this for the first neighbors connection. You have these two components that are entirely separate. So this is a word order parameter. It's like your subject verb parameter, and it's a big hub here. and it's completely disconnected to whatever is going on there. And there's a kind of, it's not an exact split, but it's true that a lot of word order stuff is happening down here, and a lot of other stuff that's not word order related is happening up there, but not entirely. Like some of these negation parameters ended up being connected here and not there. So, but for example, in the model that we were discussing, I was sort of suggesting this splitting between parameters that govern word order on one side that fix this first part of the externalization that has to do with planarization of trees, and then parameters that have to do with other properties that will filter out structures that are not compatible with those. And to some extent, so this picture, of course, is somewhat simplified because like all models are simplified. Going back to my old joke of the horses with spherical symmetry. So, I mean, this is like your first approximation model. And the thing to keep in mind is that this complete separation between parameters that have to do with word orders and parameters that don't is kind of a big approximation to make, because it's to some extent true that you do see some split of that nature, but there's some intermixing between these things even at this level. And of course, when you go now to second neighbors, you see that again there's almost this kind of it's not a bipartite structure, but it's definitely two sides. And again, word order stuff tends to be on one side, and non-word order stuff tends to be on the other side, but it's not so clear cut.
This was the only data set that had discussion about word order, or?
Yeah, exactly. So the point is that this data set already, the parameters that they sort of split between different groups, and one of them is dealing with word order, others are dealing with other aspects of syntax. So you do expect a structure that will be more consisting of separate clusters. But it's definitely, but I mean, in a sense, what is interesting is that there is some kind of intermixing between these different clusters, and there's also like here there's going to be like something that's happening in between, like these two parts, which is
Where the two may have some of the left, there seems to be two nodes that have a lot of things coming out of them.
That's right. Yeah, that's right. So there's and these are So I remember I mean, they are some of these are both some of these word order parameters. I don't remember exactly which one. So one of them is still the subject verb from the first one, and the other is something else that of course is not readable now in my picture, but
Is verb object, and the right one is.
yeah, okay, you have the image that's readable, yeah. Fine. Okay.
So this is the first thing you said today that relates back to the model that you made within the Linguistics. So you're playing around with the data, but will you also talk about how you can actually answer the question of structure using your actual, binary trees and forests?
Yeah, so of course, each setting, each of these parameters is putting some constraints, right, on your binary trees, in the sense that, for example, if I have my subject verb on, it means that, okay, I can only choose a planarization where the subject comes before the verb. And if I have my subject verb off, then I'm gonna have to choose the other one. And so some of them, so each of these is some constraint on maybe not on, so of course so linguists usually say that the certain structures or certain planar trees will trigger some parameter, in the sense that it means that structure has to be one way or another. If I switch my parameter, either the structure is okay or it's not okay. So it means that would be one of those that caught by that filter and either passes it or not. And other of my planar trees will not be necessarily caught by that filter because they're not triggering for that parameter, but they will be caught by one of these other filters and they will pass or not. So it's like each of these parameters is cutting my space of the span by the binary trees, and is cutting it somewhere. And something, is well in the subspace if I think of it as subspace, or survives in the quotient if I think of it as a filter, but it's depending on each of these cuts. So this is, of course, something where the fact that you have so many of this means that you have this very large number of filters. But of course, partly this is because you're choosing how to filter in a way that's redundant. The fact that there are so many relations between these parameters means that, of course, much fewer filters should in fact be sufficient to achieve the same result. That for a particular language you have only the survival of certain structures, but yeah, this, I mean, in a sense, what if I want to make this entirely explicit, the question is still down to understanding how explicitly one can describe these relations, right?
But is there enough data for that? Shouldn't you be trying to be less explicit?
Yeah, exactly. So in the point that I think is part of the lesson of this story, right? So here we can say, okay, I'm giving you a new set of variables, right? The eigenfunctions of the Laplacian of these graphs, and these are now a set of variables on my same that replaces my parameters. I can give you these variables, and I can also describe when these are a good set of independent variables that captures as much as possible of the variance of the original set of data, and so on. But I mean, again, now then I have a question of interpretability, in the sense that if I give you, so I could say I'm making some filters by a simpler set of variables, in the sense that now I have much fewer variables to describe, but I don't have an explicit description of what these variables mean anymore. I mean, if I'm telling you subject verb, this has a very clear linguistic interpretation. If I'm telling you that it's the first eigenfunction of the Laplacian of this graph, and well, fine, but on the other hand, I mean, this kind of so philosophical question about this, like, so we're trying to discuss describe how our brain is filtering out structures that language produces on the way on the basis of examples that we see, right, when we are learning a language. And of course, if you're learning a language as an adult, but we shouldn't be caught by the bias of what we know about learning a language as an adult. Because if you learn a language as an adult, you want information like subject verb, right? If I'm speaking a sentence, do I put my subject after the verb? But if you're learning your first language as a child, that doesn't mean anything to you any more than the first eigenfunction of the Laplacian. So it doesn't have relevance, the fact that the parameter has to have that description that reflects what you write in a grammar book for a language. It has to be something that triggers a certain filter in your brain that will filter out certain trees and will let other trees pass. And this could be on the basis of variables that are entirely different from the way that you would rationalize this process in terms of what we can verbalize about the structure of a language. So
what we can verbalize is still very explicit, right? If you're studying structure. So last time when you spoke about operand or its colored operands, and then you got into saying, okay, there's two morphisms between these non-morphisms. Isn't that the most natural way to study, least explicitly, the notion of continuity between languages?
Yeah, no, I agree. I agree with the fact. So no, what I said just now is not to say that I'm advocating giving up on trying to have descriptive variables, right, of these parameters. No, in fact, I'll finish beginning of next time saying what I think that one should try to aim doing with this. But I'm just saying that if you look at the question from the perspective of what is actually happening in our brain when we are learning a language, the fact of how descriptive these variables that set up our filters can be is in some sense, less clear a question, right? But no, I agree that no, one should, it is part of the problem is to come up with a good description of what this geometric space is. And what I mean by good description is that, for example, here, one is aiming for an embedding, a large space of parameter into which this manifold of actual possible languages is embedded. But we know as mathematicians that thinking of manifolds as embedded is a bias. It's making things more complicated than what they should be. Manifolds are not meant to be embedded anywhere. So one of the things that one should try to do is to think of this manifold of possible languages not as an embedded object on the basis of a list of parameters that describe an ambient space, but more on the basis of intrinsic properties that define the manifold itself. And then you can say, okay, you can embed it into a particular description of syntactic parameters, which are what these databases are doing. Okay.
That's the usual propaganda, right?